Yeah, you're good.
All right. Looks like you guys don't like Friday afternoons. I mean, you do, but many people don't. 75 is packed again. I don't know what happened, by the way. If you're driving away from here today, avoid 75. It's red from I don't know where to I don't know where. Don't take Archer. Anyways, okay, let's really talk about drag. So we're gonna start adding what we call perturbations to this expression. So far, we have played with this acceleration only, Keplerian force. So from now on, we're gonna start adding perturbations. So this is an acceleration because that's what we have done, accelerations. Forces per unit mass, you want to call it that way. And so let's model, we're going to come up with some models for these perturbations. So the first one we have to deal with is drag. And it makes sense because it's the first one we're going to encounter as you go up. It doesn't matter if you go into geostationary orbit or you stay at LEO, you have to go through that. So the model for that, it's no surprise actually. It is borrowed from the usual aircraft flight dynamics that you see. 1/2 density of the atmosphere is rho. A is the crosswind surface area, drag coefficient divided by the mass, because this is an acceleration. And then here we have the norm of the relative velocity that I have to define, squared. This is the magnitude, right? And it's opposing this VREL. So we're going to comment on all these pieces a little bit. So, no, 1/2 is 1/2. There's nothing to say about that. Rho is the density, the atmospheric density at pretty high altitudes. We said space starts at 100 kilometers. That definition is kind of blurry, but we need to spend a few words on the different models available. But let's do the simple ones. A is what we call cross-wind surface area. In other words, you take your spacecraft, you look at the direction of that VREL that I have to define, but it's a vector, and you project the surface of your spacecraft on the plane that is normal to that VREL. So say that this is your VREL vector at some time, and I don't know, this is the plane that is normal to VREL, right? And your spacecraft is here as a weird shape, whatever that is. You project this on that plane, and this is A. Okay? Make sense? This is your A. Projecting the entire body, the shape of the spacecraft on that plane. Okay? Yep. So the VREL should be applied at some point on the spacecraft. We're not doing attitude here. This is not a class about attitude dynamics. So we treat everything as a point, but in this case we need to know at least the surface. CD is the drag coefficient. If we are down here and we can talk about flows, then we have wind tunnels. You can take your car, you can take your motorcycle, you can take your bicycle, you can take whatever you want and have pretty good ideas of what the CD does and how it changes with the angle of attack and other parameters. What people do in space is, the simplest thing that we do is this. Just say it's 2.0. I think that's the most commonly used value for CD, unless you know something more. Actually, if you go on the page where I downloaded the orbital elements for the ISS, I think at the beginning they give you some numbers like the mass of the ISS, which is changing, evolving, by the way. And I think they give a drag coefficient of 2, if I'm not mistaken. 2.2, that's what people use. The reality is that this CD depends on many things. It depends on temperature. It depends on the roughness. I don't even know how to come up with a variable for that, or your surfaces. It depends on the chemical composition. It depends on, let's see, attitude of the spacecraft. So there are a lot of available models in literature where this CD is not a constant, it's a function of many different things, which is beyond what we want to do in this class. But it's for your knowledge to know that, unfortunately, for a spacecraft, modeling the drag force is a huge problem. Because we are engineers and we like to recycle formulas we are familiar with, so that's what we are doing here. But this is for an aircraft. So the big problem in all these variables are basically a good idea of the CD. Well, this is something you can measure, of course. The mass, you better know that. And a good model for the density. The velocity, say you have GPS, you have measurements, so you know what that is. But these two guys here are a big problem for a spacecraft. The models available for density are very different, and none of them is really accurate. And the CD is the same. There is a lot of research going on. So what people do, they run what they're called direct simulation Monte Carlo, I think. There is no wind tunnel that I know of that can reproduce the conditions of orbital flight. You have to imagine having an object in pretty much almost vacuum, just a few particles that go at 7 kilometers per second against your object. It's very difficult to create that. I'm not aware of any facility that can do that. Maybe some electrodynamic propulsion facilities can try to reproduce that, but then the size becomes the problem because you cannot do it big. So we really are struggling to this day in terms of CD and density. We have refined models, but each of them are really customized for the specific case. Now this is my bread and butter, or at least has been for a while. So if you go on my website under publications, we have some papers on using drag to control relative motion of satellites. There will be a new paper appearing soon on the Journal of Guidance, Control and Dynamics, where we do have a pretty elaborate model of CD if you're interested. We're using there in simulation. Several papers on density modeling and forecasting the density on a given orbit. Imagine what is happening. This force is affecting you. And to know where your spacecraft is going to be, you would like to know, predict everything that is in this formula. Now, up to this point, we've been able to predict this, right? You can integrate the equations of motion, and if nothing else happens, you can do a pretty good job with this. But what about this guy now? You have this force, if you can't predict what it is, then you don't know what that acceleration is going to be. You don't know where your spacecraft is going to be. To this very day, if something starts decaying and we fear that some parts survive re-entry, we don't really know where they're going to land. With a very good accuracy, we kind of have an idea, and it's usually wrong, as far as I know. So this is a pretty big deal. But for now, for what we are concerned, we need to know that this, you can assume, is a constant, roughly. There is a range, and the density is the other big problem. So yeah, VREL, well, M is the mass, of course. Let me just spell them out here. M is the mass of the spacecraft, nothing else. Then I'm going to talk about VREL. The density models. I want to spend a little bit of words on these. There are several available. I made a little list here. You start from the simplest, the US standard atmosphere, which is what I'll give you the function for. This was developed in 1976 by several places, several agencies involved. The main ones are these guys here. National Oceanographic and Atmospheric Administration. There was an extra O instead of an A. We know what NASA stands for, right? National Aeronautics and Space Administration. I was on a bus in Kennedy Space Center, one of the tours, and the bus was full of people, and the guy at the end of the tour asked what this stood for. I was in the back and I yelled, but no one else knew. No one else on that bus knew what this stood for. I'm not kidding. And they were not coming from outside of the US, okay? Well, some of them, but not everybody. And this is the Air Force. So this one, I'll give you a function in MATLAB that spits it out. It's basically telling you that density is a function of the height from the surface of the planet. So this is just height. And it's a simple formula, rho I. I'll tell you what the I stands for. That multiplies an exponential minus z, z minus zi over this hi, where hi is called scaled height, and it's given by this expression. You really don't need to memorize any of these because basically there is a lookup table for all these values that you can use. And this is natural logarithm of rho I plus 1 over rho I. So the i's, they only indicate that you start from the surface of the planet. And this would be, I guess, your I equals 0. And then there are predetermined heights. So it would be I equals 1. Don't ask me the values. I don't know. I don't remember. I equal 2, etc., up to 1,000 kilometers. And so in each of these ranges, you will use the corresponding scaled height and compute the density up to I equals 1 with this formula. Then when you get to this point, you switch the hi and use the same expression. So you basically create a table of values. and I have a function that I'll just give you. It's just a bunch of numbers that correspond to heights, and it interpolates when you enter in a different height that is not in the table. And then if you try to do something above 1,000, it will tell you, bah, I can't. Yes?
Is I equals 0 at the boundary of Earth, or is that a ring around Earth?
No, it's a surface of the Earth, I think.
Okay,
let me see. Yeah, let me think if it makes sense. I think it makes sense. I don't know if I goes from 0 to 1 or from 1 to 2. It doesn't.
Sea level?
Sea level, I think, yeah. Yeah. So I don't know if you want to count. Yeah, the I can start from 0. It doesn't make any difference. As long as you know it's chunks. But again, it's basically a lookup table. That's all you need to know. There is a lot more than that. There is more elaborate models that take into account other effects. Let's see. So that's the US standard. Then there is NRL. This is for your knowledge. We're not going to use them, but if you go into this field, you need to know this. This 00 stands for the year 2000. This stands for Naval Research Lab, and the rest I have no idea. I don't remember. M has to do with geomagnetic activity. One of the S's is the sun for sure. So this model takes into account more realistic effects, inputs into the dynamics of the atmosphere. The fact that the geomagnetic activity has an input into the behavior of density. The sun, if it's very active, makes the behavior of the density pretty messy. Instead of being an oscillation from day-night, it becomes more complicated. So this would be a little better than that. Still, if you read papers about these density models, none of them is accurate more than 30%. So they're pretty terrible because it's difficult to model them. Then there is Jackia-Bowman. This is still used. These two gentlemen, I don't know about Jackia. Bowman just retired, and we actually still have a proposal pending with him, and I hope he gets funded. But yeah. So these people are still active in the field. These things that we're studying, keep in mind, they just happened in the last few decades. Really not that much more than that. Now, the European Space Agency claims that this is the best available today density temperature model, 2013. We play with this, and so on and so forth. So look at some of the papers that we have online because they're pretty interesting. The density modeling is a big problem. Now, what is VREL? VREL is basically how the spacecraft is moving inside the atmosphere, is the motion relative to the atmosphere. That's what you do for an aircraft too, right? So it would be the velocity of the spacecraft. I'm just going to call it V, as we have done so far. So that is the V you guys create when you integrate in ODE 45 in ECI. Okay, the inertial velocity of the spacecraft around the planet minus the velocity of the atmosphere. And this, another terrible approximation that we're going to make and live with, we're going to say that it basically goes with the planet. That the atmosphere is a thin layer, a layer of glue or something on the planet that rotates with the planet, which is not true. But again, we don't know any better. We have some satellites that measure winds and strange things that happen at different altitudes, but they do it in some locations. They don't cover the entire planet. So for our purposes, this is basically what would be the velocity, inertial velocity of the point you're flying through in the atmosphere. What would that be if you're rotating with the planet? So can I erase this? I think I can, right? What do you think? It's basically just making the sphere that is our planet a little bigger, right? X, Y, Z. You would have a sphere here. You just add this additional layer on top, and it's just part of that sphere. So if my spacecraft is up here, and this is its position vector r, what is the velocity of the atmosphere at that location? Keeping in mind that this point, if I see it as part of the atmosphere, is basically rotating with the planet. So you can make the sphere bigger if you want. Just go with that. Earth rotates about its axis, right? So this is simply going to be angular velocity of the Earth with respect to the inertial observer, which would be ECI in our case, crossed with r, nothing else. So that's a pretty simple model, but that's what we do. Let me see what else I want to tell you about this, other than running an example in MATLAB. where I show you how to basically, you add that acceleration and then we move to something else. So in our work in the lab, if I have time, I'll show you at the end. What we do is we assume that we have satellites flying. One of the things that we do, flying in atmosphere, spacecraft 1 is here. Spacecraft 2 is pretty close to it. So let's just say that there are two little cubes, spacecraft 2. And then in some way, these two have some surface that they can open and close. So at some point, say that they're flying in this direction, spacecraft 2 can open a sail in the back, a drag sail, some surface that makes it experience more drag. What happens there is that they have differential drag now. One is experiencing more drag than the other, which means it's going lower faster than the other. A faster orbit means what in terms of velocity? Lower orbit, I give you the answer. Lower orbit means faster, right? Smaller radius, so it's actually catching up from below. So we play with these surfaces to rendezvous the satellites using only drag if the two of them have controllable surfaces. And as I told you, this is, people are doing it not for fine rendezvous maneuvers, but they do it for constellations. They use the drag. So it is unfortunately bringing down your orbit, but can also do something useful if you use it wisely. So I just have, let's see, what do I have? I think I have an ISS with drag software that I created just to show you what happens. So this takes basically the function with J2, adds the drag. Where are you? Okay, here it is. Let me see. Drag, J2 and drag. Okay, so I have a few drag parameters here. I'll comment on those in a second. So I'll give you this. So this is going to be my drag force. And as you see, if the height is less than 1,000, this is the function that I'll also provide you. Get density basically takes that US standard model. You just give it a height. So it's radius minus the radius of the Earth. And it just gives you a density in kilograms per meters cubed. You need to be careful with that. So I just have a check here. If the height is less than 1,000, you can do this. Otherwise, forget about drag. This function is going to give you nothing, 0. There is basically no drag, right? So 1/2 density. So just this thing is basically raw. CD, I gave a 2 surface over the mass, and this is the norm of VREL times VREL itself. And then that 10 to the third is just to make it dimensionally meaningful because I had other units. And then where is VREL? This is VREL. Let's see. Yeah, velocity is the last 3 components of my vector coming in. Velocity of the atmosphere is the omega of the planet on the z-axis. That's why I have 0, 0, 1 crossing with r, which is x, y, z. Makes sense? And subtracting the 2 gives me the VREL. So I'm basically doing exactly what I told you. Yes?
Are you missing a square in the...
Am I missing the square in the V?
Yeah.
No. That's the way I'm doing it there. Instead of doing VREL. Oh, yeah, I'm missing something here. I'm sorry. This is the unit vector, yeah. Yeah. Correct that. Thank you. Make sense? So this is the magnitude of the drag force. Forget the minus and forget the vector. It's 1/2 density surface CD over mass VREL, the normal VREL squared. Okay? But then this is just telling me that it's in the direction opposite to VREL. So this is the unit vector on VREL.
No, I'm saying in the code. I think you're missing the square.
Right. Or another way to write this is normal VREL times VREL the vector. It gives you the same thing. If you're multiplying VREL squared times the unit vector along VREL, or the normal VREL times the vector VREL, you get the same. Yeah, it's just another way. Yep. Yep. And so I have 2 cases. The first one, which I'm not entirely sure about because I completely made up the surface of the ISS. I couldn't find an accurate number. If you go on their website, they give you some mass that it's 410 tons for the ISS. The CD is 2. The surface you can find, I mean, it depends on the orientation of the panels. It depends on many things. I just said it's 1,000 meters square, which is probably too much. But if and this is a little CubeSat, by the way, that we have, but I'm going to run it afterwards. So if you take exactly what I've done, for homework 2, the same initial orbital parameters, the same date, I convert into state vector x and y here, x, y, z. And I'm doing it for just 15 hours. But now I'm calling that function. And I call the function without drag, just to compare what happens. So this is going to pull up, hopefully, the behavior of the trajectories if you have, if you have drag or if you don't, just to see what changes. Yes, okay. This is with drag, I believe, the blue one. I know altitude looks like it's going up, but that's because of J2. It does oscillate. If you run it for longer, it actually goes down. So this is argument of perigee. You don't see much of a difference. This is the REN. You see no difference, pretty much. These inclinations, too much stuff on the same plot. But the one where you do see some difference that I really care about is the same major axis. It's the blue, again, is the one with the drag. So with no drag, same major axis oscillates between those two values a little bit because of J2, but with drag is steadily going down. So you lose, in terms of semi-major axis, you're losing what? A kilometer, not even, in 15 days. But that's with that surface. Again, I'm not entirely sure about that surface, but just to give you an idea of what is going on, you're losing energy, right? That is the point. And these are the two trajectories on the same planet, which is terrible. But that's what it is. Now, if I switch to something I know a little better, which is our tiny spacecraft here, look at what happens. So this is our CubeSat, and we do have an idea of its, it will have a sail in the back that can open and close. At the maximum deployment, we have 0.25 meters square of surface. Like this, not that big. CD is the same, I don't know any better, and it's 5 kilograms at the most. It's a 3U CubeSat. These will go down much faster because it's a small mass, and so the ratio between these two matters a lot, as you can imagine. So if it does run, I hope it's running. Yeah, it's taking its time. So this is with drag, see? That's the altitude here is not even thinking about oscillating a little bit, just going down consistently. J2 is there, but the effect of J2 is completely overcome by the drag. So those two forces are comparable usually for some types of spacecraft, but when you get something that it's basically, it's just coming down because of drag, this is what you get. Altitude is consistently going down. Yeah, these are the orbital parameters. You're not going to see anything different. Inclination a little bit. Eccentricity is changing, but see the same major axis is collapsing. This is not going to last long if we just leave it with the sail open, which of course we're not going to do all the time, but that's what happens. Any questions? Drag brings down your orbit. Smaller and smaller energy. Yes?
So when you use that parachute, they were just bringing you down to a different level and then close the parachute?
Yeah, well, the idea is that for now we're building one CubeSat, but if you have two of them, you will do this game of opening and closing between the two and focus about the relative motion, which I hope we get to talk about a little bit. Rather than focusing, this is all absolute motion. This is with respect to the planet. What we're trying to do is control their relative position with drag. So they're both going down in the same time, probably at the same rate, but at least we can control their relative position with these drag surfaces. Another project we have is trying to come up with profiles to open and close some drag device in the back so that you can have an idea of where, again, the spacecraft is going to impact the ground if something survives, or at least leave space, like at the threshold of 100 kilometers, you know more or less on which latitude and longitude it is. But that's difficult to do. But that's something. It is something of interest not only for decaying satellites and things that can survive re-entry. If we're going to Mars, for example, and you have to land something and you want to know where it is, it would be nice to have a good knowledge of the drag force and the way to use it. But again, it's difficult. Questions, concerns? I'm going too slow because I wanted to do J2 as well. No other questions? Yes?
Does this apply in respect to like geostationary satellites?
Oh, of course not. After 1,000 kilometers, forget about drag. There's no atmosphere. There's something else going on. Solar radiation pressure will be your first non-gravitational perturbation. Blah. I hate chalk, by the way. Is the sound still working, Padre? Mm-hmm. Okay. All right, so let's start with gravitational perturbations now, and I'm going to remove that soon. So, what do we do here? We do the following. At some point, we talked about this scalar function, which is our potential function, right? And we said if I compute the minus the gradient of this, which is, by the way, partial of v with respect to xi plus partial of v with respect to yj plus partial of v with respect to zk, okay? I, j, k, x, y, z are ECI axis. We said this is going to give me my force. Okay? Well, what people do, people much smarter than I am for sure, what people have done is they said, well, if I have a shape that is not a sphere anymore, I'm going to add something else in this potential function. So, to take into account the fact that the planet has a weird shape which is not a sphere, we have the spherical potential part plus some other capital Phi potential that has been defined for us, and people have done it by using intelligent math and mostly satellite measurements, by the way, satellite observations of how the trajectories were going away from the nominal one. That's how they built this potential function. So to do so, to define in particular the potential function that has to do with the oblateness of the planet, the fact that the planet is not a sphere, it is convenient to use, well, this is ECI, right? But to use spherical coordinates, and it should be clear in a second why. So if this is the planet, and now try to imagine that this is an ellipsoid now. At the poles, along the z-axis, I am pushing this ball, so I create bulging at the equator. The line of the equator still remains a circle, even though that is not true. But that's a first approximation that it's better than assuming it's a sphere. The poles are closer than 2 points at the equator. And so this is a perfect ellipsoid in first approximation. And so I'm going to try to talk about potential of that. Now, if my satellite is here, at a certain distance from the center of the planet, I'm going to use what people have used, because it makes it convenient, spherical coordinates to define that phi, that potential that I'm missing, where the first, well, r is one of the spherical coordinates, of course. This angle phi is the second one, and then this angle theta, as you project the spacecraft on the xy plane, is the other one. So this will be a function of, in principle, r, phi, and theta. Now, if that's an ellipsoid, a perfect ellipsoid, oh, I closed MATLAB, but I should have left it running probably. What do you imagine this to be a function of in reality? If I'm only taking into account the fact that this is not a sphere anymore. Or in other words, as you're flying around the planet, imagine that as you get closer to the equator, you see a little more mass. There's a bit more belly there, and a little less as you go over the poles. Is theta going to matter? It's all symmetric, right? If it's symmetric about z, this is gone. And I'm going to give you what this is, because again, people have done it for us. And the way this was built, again, is by very smart mathematicians combined with people who were observing motion of satellites. So this is an infinite series, as usual. When we don't know exactly what to do to model something, we end up having infinite series. Jk r over little r to the kth power, and this is pk cosine of phi. Can we see this, more or less? All right, this is the usual mu over r, there's nothing else to say. This is a counter that goes from 2 to infinity. These are called zonal harmonics, J2, 3, and 4, etc. This is the radius of the planet at the equator, because now we don't have a radius because it's an ellipsoid. This is, again, r, the position of your satellite. And these are the Legendre polynomials. And I think I do have the expression for those if you're interested. The pk of a function x would be this. Just for your knowledge, we're not going to use this. Because we are engineers. You see an infinite series, what do? Stop at some point, right? You can't use something like that. And as a matter of fact, the j's, again, these j's in particular, these are constants, are a-dimensional constants. Those in particular come from satellite observations. People have looked at how satellites move in reality, and with data they've been able to put together this expression. And still, as of today, we have some spacecraft that try to map the gravitational field, like the GRACE mission, which I have probably mentioned before, to update these J's, to give us better J's. But the reality is that we stop at J2. Because everything else, the other J's after J2, they are orders of magnitude smaller, so do they matter? They matter if you do numerical integrations for a very long time, very, very long time. And probably, drag or something else has taken over anyways, so they're not that critical. So the J2 one, let's see, where do I have it there? There it is. So the phi, this phi potential that I have to, by the way, start differentiating at some point, it's almost equal. It will be equal to that infinite series, but we stop at J2. It's going to be J2 over 2 mu over r. This ratio is there. And then I have 3 cosine squared of phi minus 1. I think, well, the J2 value, I don't think I wrote it down here, but it's in your code. It's a given constant, okay? So what do I do with this now? I want to do exactly what I've done in my drag program, where, let's see. Well, yeah, what I've done is r double dot equals minus mu over r cubed r. I want to add now a perturbation acceleration due to, let's just call it J2 now, the oblateness at the poles. What do I need to do? For the drag, I just gave you the acceleration. I didn't have to do anything. It's a model that people use. For this, I have a potential function. So what do you do with that? Again, this is not really needed. Maybe this is. Yeah, let's leave it there. What would you do if I gave you a potential function to compute the corresponding force, or force per unit mass acceleration? Well, the perturbation due to drag is going to be equal to the gradient of that, right? Exactly like we've done before. And now the fun begins. Because, how do you do that? This will have to be partial of the capital phi with respect to xi plus partial of phi with respect to yj plus partial of phi with respect to zk. Okay? But the phi I gave you, right there, is not a function directly of x, y, and z. So we're going to do this one, and then the rest it just follows, the procedure follows. But just for fun, we're going to do this one. The partial of phi with respect to x. Since I don't have an expression, a direct expression of phi in x, I will have to do this. I will have to compute the partial of capital phi with respect to r, I see r here, times partial of r with respect to x, plus the partial of capital phi with respect to little phi, the angle, times the partial of little phi with respect to x. Chain rule, right? Okay? Now, what do we know? We know the following. We know that phi, by the way, it's given by some relationship here. Phi will be the arctangent of square root of x squared plus y squared over z, if I'm not mistaken. You can prove that to you. Yeah, that makes sense. Basically, what you do, you're going to look at this triangle here, right? These two sides. This is x square root of x squared plus y squared. This is z, and you can figure this out. So I do have a relationship between phi and the Cartesian coordinates. That's nice. These two I should be able to compute. What is dr in dx? Let's do that. Let's just start from that one. I think that's the easiest actually. How would you compute dr in dx? Not even a hint? That is not a vector. R is not a vector, it's a scalar. It's appearing as a scalar, so, and it's not a time derivative. What is R? In Cartesian coordinates, if you want to take a derivative, a partial derivative with respect to a variable, you better have the expression of that function in terms of that variable. Somehow you need to get to that, to the bottom of that, and being able to do it, right? So how do you do this? dr dx. Well, it's 1 over 2. The square root goes down here, right? X squared plus y squared plus z squared, and then the partial of this with respect to x, which is 2x. And so this really ends up being x over r. You see that? No? Yes? Okay. So that's really the easiest one. Let's do now, so I still have to do, well actually I have to do partial of phi with respect to, yeah, that. Now how do you do the partial of phi with respect to x? That would be the partial with respect to x of that ugliness there. And I think I'm going to give it to you. I'm just reminding me, because I don't memorize, the d dx of the arctangent of x. Do you remember what this is? This was something like 1 over 1 plus x squared, right? So starting from that, you do the partial of these. The argument of the arctangent goes down here, manipulate it. What you get is, let's see what we get. Okay, the first step is this, xz over x squared plus y squared plus z squared. Okay, we believe that. Now, I do recognize some familiar things here, I think. What do I recognize? This is r squared, right? And then I'm going to do this. 1 over square root of x squared plus y squared. I'm going to divide by r here and make this an r cubed, because that gives me something that I should be able to see. Let's see. What is that? Okay, look at this angle here. The pi minus phi, right? This side, I don't know what to call it. Let's give these names. A, B, and C will be my spacecraft, right? So the side AB is equal to the side AC, right? Times what? Times the cosine of pi over 2 minus phi, right? Now the side AB is that square root of x squared plus y squared. The AC is r, and the cosine of pi over 2 minus phi is sine of phi, right? So in other words, I do recognize the sine of phi down here, right? I know this is a lot. I'm going to skip a lot of steps here because it's kind of a lot of math, but that's what it is. Okay. So I do have these, and I do have these, and then the other ones are not too bad. Do I still need these? I don't think so. Oop. Maybe I should leave this for a while. What is the partial of the big phi now? Which one do you want to do? With respect to r. What is it? I don't need this anymore. Well, it's right there, right? Consider everything else constant except r. I see an r and an r squared. Don't ask me why it's in this form, just because if I keep it in that form, you're going to see the formulas that I gave you in the MATLAB code, because that's what people usually use to present the J2 acceleration. So that's just convenience. So that's an r cubed that I see at denominator. So that's going to become a minus 3 over 2 mu over, now I'm going to see an r to the 4th at the denominator, so let's just leave it like this. Yeah. Okay. And then partial of phi with respect to little phi. Now, everything else is constant except phi. So that gives me, the 2 will go away, that will give me a minus 3j2 mu over r, big R over little r squared. I have a cosine of phi and a sine of phi. The minus is coming from the derivative of cosine, which is minus sine. You see that? And the 2 is gone, and it's simplified with the other 2, and the 3 is coming from the 3 that was there already. So I think, pretty sure, unless I forgot how to do these simple derivatives, that your book has a divide by 2 here, and that is a typo. I think. It wasn't making sense to me, but double check. I may be wrong, but I think that's what you get. So now you have to basically multiply all these things together, right? Yeah, let's do it here. And this is only one on the x direction, so I'm not going to do the other ones. The partial of phi with respect to x is now all these things together minus 3 over 2 j2 mu over r squared big R over r squared 3 cosine squared of phi minus 1. I think now you understand why I was waiting to do this one, right? It's just to show what the procedure is, but in the end, the idea is you have a way to write the potential, and then you have to take its partials. Yeah, x z over r cubed sine of phi. So this sine of phi goes away. I don't think we're going to use this anymore. Okay. Believe me, this is another relationship that is useful. Cosine of phi is also z over r. If you redo your triangle, you're going to find out that. Okay. So we substitute that where we see cosine of phi. Let's see what we get. I have a minus 3 over 2 j2 mu over r squared big R over little r squared. I'm still looking at the first one. So this becomes a 3 z over r squared. This is the cosine of phi, right? Minus 1, that is still multiplying this x over r, plus, well, minus, plus minus, 3 j2 mu over r squared. Well, I simplified everything already. Let me not skip too many steps. Okay, mu over r, big R over little r squared, and those are the first ones. And then I have a cosine of phi that becomes a z over r, right? And then I have another z over r that I'm extracting from this thing here. And what I'm left with is what? Is an x over r squared, right? You see that? Yes?
Can you really quickly one more time go over why I'm getting lost, really lost in the math as to why we're...
Yeah, that's why I'm going to do it only for this one. So the high-level idea is that thanks to satellite observations and just imagining that our spacecraft, our planet is an ellipsoid, we can say, okay, the additional perturbation that I have because of the fact that this object is not a sphere anymore is some potential, I can express it as some potential function which only depends on r and phi. I'm sorry, not theta, this is phi. We agree on that because of symmetry. Take an ellipsoid, the z-axis is the symmetry axis, the theta doesn't matter. And now I gave you some formula that we believe that that is the potential. And now I'm taking its partials with respect to x, the x direction, the y I'm not going to do it, the z I'm not going to do it, just showing how to do that. But since this is expressed in spherical coordinates, I have to do all these intermediate steps because I want the partials with respect to the x, the y, and the z, not with respect to the r and the phi. So I have to, in the way of doing this, I have to find the partial of r with respect to x and the partial of phi with respect to x, and so that all this pain comes from there. So, but is it high level making sense? I want to show it at least for one component, because we'll be talking about this J2 for too long, and it's about time to show where it comes from. So what I've done here, 3 J2 mu over r over r squared, cosine of phi has become a z over r, sine is gone. Then I take another z over r from here, I am left with an r squared, and that's what I have. And so in the end, this is z over r squared, right? And this x over r is the same, and I just put the square here. So you can finally see that they're very similar, sum them up, and get what you have in your code for the x direction. Five x over r squared minus 1. So if you look at my MATLAB code, except the minus, of course, this is the partial with respect to x, so you'll have to change the sign. This is the x acceleration, right? This is the perturbation in the x direction if I change the sign. So this is the minus perturbation in the x direction. Look at the code. I think we still have a few minutes. Maybe I'll project it again. But that's how you do it. So same kind of procedure follows for the y direction, the z direction. There is more to say. This is just squeezing the planet. The planet is not just an ellipsoid. The equatorial line is not a circle. So the bumpiness of the planet is also changing according to longitude. So there is really no symmetry because of theta. So there are more harmonics that you can include. There are more refined fields for gravity where theta is also there. And so there will be other j's or other constants that people have computed that are called sectorial harmonics, where depending on where you are, it's like the slices of an orange. Depending on where you are longitude-wise, you may have more mass underneath you than at a certain location than somewhere else, because that's how the planet is made. On top of that, there are tesseract harmonics that focus on specific, I don't know if I can call them squares, but really areas, ranges of latitude and longitude. There are very specific locations on the planet where, I don't know, there is more mass. There are more mountains, for example. And so these can become very, very complicated. And it is. If you go on the website of the GRACE mission, that's what exactly they're doing. They're mapping the gravitational field to give us more and more terms in the potential so that you can have a better model for the gravitational field and have more accurate orbit propagations. But as far as we are concerned, doing J2 is good enough because it's affecting the ISS heavily, it's affecting everything that is in LEO along with drag. So it's the first one you need to know of. Make sense? But again, unfortunately, Keplerian orbits are great, but they don't exist because of the planet being in a very weird shape. Go online and check it out. I'll try to find that image. There are several 3D images of the planet that try to show the current shape that we know of, and it's very strange. So again, these are zonal harmonics is because of the oblateness, and then the sectorial are on the longitude. We're not going to see them, but you need to know they exist. And then tesseract are going to look at specific locations on the planet. I'm assuming that probably around the Everest there must be a very dedicated piece of the gravitational field, right? Is it turning on? I think we're done. I was going to show you the example, one of the examples in the book, example 12.2, which I invite you to do, because I think I found a typo in there as well. The angular momentum they have doesn't match, oh, the same major axis doesn't match what I get. But this is just to confirm once again the effect of, this is going to run very quickly, the effect of J2. It does, and I will determine those analytically with the Gauss variational equations, but what it does is going to give you a secular increase in this case of the argument of perigee. See, there is oscillations, but it's steadily going up for this particular example. and the right ascension of the ascending node is also steadily going down in this case. So those are the main effects of J2 on your orbit. The other parameters oscillate, but these two have a clear trend in one direction or the other. Okay? I guess that's it for now. Have a good weekend.